Namaskar. Today we will study beta 2 adrenergic receptor, which is a type of G protein coupled receptor, a type of GS, where the subunit is alpha S, and when alpha S subunit is activated, alpha GTP will bind to the effector adenylate cyclase. So adenylate cyclase is the effector here. So just let us recap the G protein coupled receptor. So without the ligand, alpha GDP is there. When the ligand binds, GDP-GTP exchange occurs. Alpha GTP and beta gamma will separate from the receptor and will bind to their specific effectors. And after binding, there will be activation of the GTPase, which will dephosphorylate the GTP, and alpha GDP now will get dissociated from the effector, and similarly beta gamma will also be simultaneously dissociated from its specific effector, and they will return back to the receptor and resting state will again come back. This is the cycle in which G protein coupled receptor functions. And in case of GS type G protein coupled receptor, it activates the adenylate cyclase enzyme, and beta 2 is a type of GS type of G protein coupled receptor, where adenylate cyclase is the effector enzyme which converts ATP to cyclic AMP, and the cyclic AMP acts as the second messenger. So when adrenaline, the agonist, binds to the beta 2 receptor, there will be formation of alpha S GTP, which will bind to its specific effector adenylate cyclase. Adenylate cyclase will convert ATP to cyclic AMP, and the cyclic AMP then activates the enzyme protein kinase A. And how this protein kinase A enzyme is activated? This protein kinase A enzyme has two regulatory subunits and two catalytic subunits. Cyclic AMP binds to each of the regulatory subunits. So 4 cyclic AMP can bind to these two regulatory subunits, and it will release the catalytic subunits which are active. So active catalytic subunits. When we say protein kinase A is activated, that means these two active catalytic subunits are released to produce the cellular function. So in case of beta 2 receptor, this protein kinase A, active protein kinase A, will phosphorylate the enzyme myosin light chain kinase. So let us see first what is this myosin light chain kinase and how it functions. Myosin light chain kinase enzyme, if we see, it has two sites to which calcium calmodulin complex can bind, and that will activate this enzyme myosin light chain kinase. And this active myosin light chain kinase will phosphorylate myosin light chain, and myosin phosphate will be there, which will bind with actin. Actin myosin binding results in contraction of the smooth muscles. And when this myosin light chain kinase is phosphorylated, it will decrease the affinity of calcium calmodulin here. So when this enzyme is phosphorylated, calcium calmodulin binding cannot occur with it, so this cannot be activated. So you can see protein kinase A activated by cyclic AMP through beta 2 receptor activation phosphorylates myosin light chain kinase, and that phosphorylation decreases affinity of MLCK for calcium calmodulin. That decreases the catalytic activity of MLCK. There will be no phosphorylation of myosin light chain, no actin myosin binding, and there will be relaxation of smooth muscles. So you can see in case of smooth muscles, actin myosin binding results in contraction of the smooth muscles, and actin is a part of your thin filament. This is actin, and myosin is a part of the thick filament. For each thick filament, there are 10 to 15 thin filaments. So when this actin myosin binding occurs, the myosin heavy chain, and this is myosin light chain. This is myosin heavy chain, this is myosin light chain, and this myosin light chain is actually phosphorylated. phosphorylated myosin light chain will bind with actin. Actin myosin binding will cause the contraction of the smooth muscles. So here you can see for each thick filament 10 to 15 such thin filaments are there, and when there will be binding, that will cause the contraction. And cyclic AMP by activating protein kinase A will phosphorylate MLCK and decrease affinity of MLCK for calcium calmodulin. So there will be no activation of MLCK, and that decreases the catalytic activity, and no phosphorylation of myosin and no actin myosin binding, so relaxation of smooth muscles. So in this way these beta 2 receptors function, and beta 2 receptors are located in the blood vessels supplied to skeletal muscle. So sympathetic stimulation in other areas causes vasoconstriction, whereas in skeletal muscle it causes vasodilatation. And beta 2 receptors are also present in bronchial smooth muscles. So beta 2 agonists act as bronchodilator, and we can use them in asthma. We can use them in bronchial asthma. So beta 2 agonists can either be short acting or long acting. Short acting beta 2 agonists are salbutamol, terbutaline. Long acting beta 2 agonists are salmeterol and formoterol. And beta 2 antagonist example is alpha methyl propranolol. So this is all about the beta 2 receptors, the mechanism in which it functions, the pathway, adenylate cyclase and adenylate cyclase and cyclic AMP pathway, and the cyclic AMP acts as the second messenger for this beta 2 receptor. This is all about beta 2 receptor. Thank you.